Hello everybody, it's time for our sixth video lecture. Our sixth lecture, it's time to be videotaped as well. And last time we got a homework assignment, so I want to remind everybody that homework number 1 is due on Friday. That's this coming Friday. And you will get a chance to rewrite problems. Okay? So I will grade it over the weekend and hand it back to you and give you what you've scored out of each problem and then give you a chance to rewrite anything that you missed any points about. So you can resubmit. Okay? So it's giving us a chance to get used to writing proofs. Okay? And I'll do that for the second assignment as well. But then from then on, the third, fourth, and fifth, no rewrites.
Will we be leaving comments on our homework where we can improve on the proofs?
Yes. I'll say that this doesn't follow, circle things, say that this is untrue, and give examples of why it's not true if something's untrue, and also give hints on the first two assignments. Maybe look at it this way. Does anybody want to ask anything about the problems? Anybody want to ask anything about the problems? Remember, they were all from the book, so we're trying to prove it. Now, first two problems that I assigned have 4 parts, and each one of them is kind of not every one of them, but they're a little bit technical in terms of you've got to progress kind of slowly to make sure that each step that you say follows from something we've either done or follows from the previous step in the proof. Okay? So I'll be careful with that. Anybody with a question or comment before we go on to new material? Okay, well then let's go ahead and get started for the lecture for today. And so today I hope to talk about corollary to the triangle inequality. So I'll write down the triangle inequality and then write down the corollary, which has 2 parts. And then I want to talk about extending the triangle inequality. And then I also want to talk about epsilon neighborhoods, what they are. And then we're going to move on to upper and lower bounds for sets, and what does it mean for a set to be bounded, and work towards what's called the completeness property of all. But first of all, let's recall the triangle inequality. And here's what it said. What it says is, if A and B are real numbers, then the absolute value of A plus B is less than or equal to the absolute value of A plus the absolute value of B. So that's our fact, it's the triangle inequality. And the corollary, so that's old, this is new. The corollary for this, having 2 parts, is the following. It says, if A and B are elements of real numbers, then we have 2 things we can write. One is the absolute value of the absolute value of A minus the absolute value of B is less than or equal to the absolute value of A minus B. And part B, the absolute value of A minus B is less than or equal to the absolute value of A plus the absolute value of B. So those are 2 separate things that I want to prove. Let me make sure I wrote down everything correctly. I did. And let's go ahead and prove it. Okay. So to prove, we're going to let A and B be real numbers. So for any 2 real numbers, these statements are true. Here's part A. For part A, we want to show that the absolute value of the absolute value of A minus the absolute value of B is less than or equal to the absolute value of A minus B. Okay, well here's the way I'm going to start this proof. I'm going to say, note, if you just take the absolute value of A, just this quantity in itself, well that's the same thing as the absolute value of A I'll say plus, or I'll say minus B plus B. So really, I'm adding to a 0 right here. But I'm adding, the form of 0 that I'm adding is minus b plus b. I could think of a minus b as one number, and b is the second number. And so I'm thinking if this is one number, this is another. By the triangle equality, this could be less than or equal to the absolute value of the first number plus the absolute value of the second number. So subtracting the absolute value of b from both sides, that would say that the absolute value of a minus the absolute value of b will be less than or equal to the absolute value of a minus b. Okay. That's one thing. I'm going to star it, and I'm going to do something similar. So we're going to remember that result. That's an important result for our program. Similarly, I'm going to do the same thing that I just did, except I'm going to work, instead of starting off with absolute value of A, I'm going to start with absolute value of B. So the absolute value of B is equal to the absolute value of B minus A plus A. Let me write it that way. So again, I'm adding 0 in a funny form. And then that's less than or equal to by the triangle inequality. So this is by the triangle inequality. And similarly, this is by the triangle inequality. It's less than the absolute value of A minus B plus the absolute value of A. And so if I subtract the absolute value of A from both sides, I get the absolute value of B minus the absolute value of A is less than or equal to B minus A, which I'm going to tell you is the same thing as the absolute value of A minus B. Maybe I'll take my time about this and say, well, that's the same thing as minus A minus B. Minus is minus 1, so that's equal to the absolute value of minus 1 times the absolute value of A minus B. But what's the absolute value of minus 1?
1.
Right, so I just get A minus B. Okay, so I'm going to keep working with this just a little bit. So from this line, from that last line, I'm going to go back to this. We'll turn the camera around in just a few seconds. Let me progress just a little bit. From this last line I've written, if I multiply both sides by minus 1, what I get is the following. If I multiply both sides by minus 1, so I got minus 1 times the quantity, the absolute value of B minus the absolute value of A. I switch the sign of the inequality. This greater than or equal to. Here would be minus the absolute value of A minus B. So for those of you in the class, I'm multiply this by minus 1. I have to switch the sign of the inequality, and I'm multiply this by minus 1. I get exactly what I've written. Okay. If you distribute this minus 1, what we get is the absolute value of A minus the absolute value of B is going to be greater than or equal to, or I'll rewrite it this way. I'll write down the smallest thing first. So minus the absolute value of A minus B is going to be less than or equal to, this side here is going to be the absolute value of A minus the absolute value of B. I'm going to star it, double star. If you look at our two starred statements, so there's the double star, and I'll just write below. Recall, what we had is that we had the absolute value of A minus the absolute value of B is less than or equal to the absolute value of A minus B. Okay, that was star. So if I look at these two statements, thus, if I rewrite one statement, compound inequality involving the absolute value of A minus the absolute value of B, which is both right here, what I get is minus the absolute value of A minus B is less than or equal to the absolute value of A minus the absolute value of B, which is less than or equal to A minus B. That's where I am. I'm going to stop. Let's give that back a second. Okay, here's what I want to point out to you. I've got some quantity less than or equal to some non-negative number but yet bigger than or equal to the minus of that non-negative number. Okay? So this is kind of this situation. Right here is to the side, I'll just rewrite this. This is where we have minus C is less than or equal to A is less than or equal to C. Where C is being played by the role of A minus B inside absolute values, and A is being played by the role of the absolute value of A minus the absolute value of B. Is that okay with everybody? That's exactly what I've got. Well, we got a statement about this. This happens if and only if the absolute value of A is less than or equal to C. So here, I'm saying here's my A, so this is really, the conclusion is, therefore, absolute value of A minus absolute value of B is less than or equal to the absolute value of A minus B. And that proves part A. We still got to do part B. But I'll step back. So, showing that an absolute value quantity is less than a non-negative number, we use this back here quite often. That was part C of a theorem that we had before. You know, that's a good thing that theorem gave us, part C. It gave us a way of showing that the absolute value of something is less than a positive number, non-negative number. It showed us how to do it. So you got to show this, which is what we just did here. Okay. Part B. So for part B, let's remember part B. We want to show what do we want to show? We want to show that the absolute value of A minus B is less than or equal to the absolute value of A plus the absolute value of B. That's what we want to show. Here's the way I'm going to think about it. I'm going to say, well, note, the absolute value of A minus B is the same thing as the absolute value of A plus minus B. Because that's the way subtraction is defined. But that's less than or equal to, by the triangle inequality, the absolute value of A plus the absolute value of minus B. Now from homework assignment, the first part is absolute value of A, but homework assignment would say, well, minus B is really the same thing as minus 1 times B inside absolute values. Then a theorem we had earlier, absolute value of A, I'm just writing down, but plus, when you have the absolute value of a multiplication, this was part A of the theorem, that's equal to the absolute value of the first guy times the absolute value of the second guy. What's the absolute value of minus 1?
1.
That's right. And so 1 times the absolute value of B is absolute value of B. So here, we have this initial starting point, A minus B inside absolute values, is equal, but then it's less than or equal to. So overall, this guy is less than or equal to the ending part here, which is the absolute value of A times absolute value of B. That's what I wanted to show, so that is that proof. Those are two corollaries using the triangle equality. Here's where the triangle equality was used in part B. Okay, I want to extend the triangle equality. The triangle equality is a statement about absolute values of two real numbers being added together. But really, you don't have to have just two. You could have more than two. Is that okay? So here's the way the statement is given in the book. It's a corollary as well to the triangle equality. It says, if A1, A2, up to A sub n are real numbers, then the absolute value of A1 plus A2 plus, you keep on adding up to the nth real number, that's less than or equal to the absolute value of the first number, plus the absolute value of the second number, plus you keep going, all the way up to the absolute value of the last number. Audra, I said this extends the triangle equality. the triangle inequality, n would be equal to what? N represents the number of numbers involved. In the triangle inequality, how many numbers do we have involved? Do you remember what the statement of the triangle inequality was? It said if A and A and what?
B.
How many real numbers do you have? No. You just had A and B, just two. Here, how many do we have? We have n. So here, in the triangle inequality, our n was just 2. This statement is more general, okay? In the triangle inequality, n was equal to 2. Okay? We only have 2. Here we could have 50. N could be 50, and this is still true. So, this is a statement that makes the triangle inequality true for any n, where n is a, what kind of number? No?
Natural number.
Natural number, not real. Natural number. So this is a statement really about natural numbers in some sense. Is that okay with everybody? What's a good proving method for statements about natural numbers? Induction, and that's why I'm going to do this. So, okay, we will prove this by induction. So I'm going to prove it's true when n is equal to 1. Okay? So when n equals to 1, what's the statement? Well, it's
absolute value of a sub 1 is less than or equal to the absolute value of a sub 1.
That's correct. Beautiful, Corey. So the left-hand side, we only have one term involved, the absolute value of a sub 1. And on the right-hand side, we only have one term involved, the absolute value of a sub 1. There's only one thing. So the statement is like vacuously true. Okay? So I'm going to say when n equals to 2, not that we had to show this, but really it's going to be beneficial for us last time. We know that a sub 1 plus a sub 2 is less than or equal to the absolute value of a sub 1 plus the absolute value of a sub 2. And the reason that I already know that is because this is the triangle. Okay. As this is the triangle. Okay. We usually don't show n equal to 2, but I did here because we're going to need it. That's why this statement's a corollary. I'm just reminding us we've already shown it. So Chuck, in induction, what do we do next? We assume the statement is true for n equal to... No? We've proved it's true for k. So next we assume the statement is true for n equal to k. Okay? What is the statement then? What is the statement? That is, I know the absolute value of a sub 1 plus a sub 2 plus all the way up to a sub k, there it is less than or equal to the absolute value of a sub 1 plus the absolute value of a sub 2 plus the absolute value of a sub k. So I know that. What do I want to show?
That the absolute value of a sub 1 plus a sub 2 plus all this a sub k plus a sub k plus 1 is less than or equal to the absolute value of a sub 1 plus the absolute value of a sub 2 plus all the way up to absolute value of absolute value of a sub k plus the absolute value of a sub k plus 1.
You said it a lot, very well, Corey. You said it with a little bit more detail than I'm going to. So that's what I'm going to write down, is what we want to show. And now I'm going to start here. So Corey said, hey, don't forget about the a sub k. Well, I did forget about it, but I'm going to include it now. So I'm going to take a look at that left-hand side. I'm going to say, no, the absolute value of a sub 1 plus a sub 2 plus all the way up to a sub k plus 1 is really the same thing, not less than, I'm not looking at this right-hand side. I'm still looking over here at this left-hand side. That's what I'm concentrating on. It's a sub 1 plus a sub 2 plus a sub k. Melissa, that's the thing right before a sub k plus 1. And then plus a sub k plus 1. Dalvin, I'm going to think of a sub 1 added all the way up to a sub k is one number. That's just one thing. Whatever it is, that's the way I'm symbolizing. And Adam plus a sub k plus 1 is another number. So, Chuck, this is one number, Right here, John, this is another number. When you take two numbers and you add them inside absolute values, I know by the triangle inequality, that's going to be less than the following. It's going to be less than the absolute value of the first number plus the absolute value of the second number. Okay? So what's the absolute value of the first number? What do I mean by the first number in here? It's the absolute value of what? Anybody? Plus the absolute value of a sub. Okay, and that's by the triangle inequality. Is that okay? So for those of you here in the room, this is one number. Look, this is one number plus another number. That's less than or equal to the absolute value of the first plus the absolute value of the second. That's by the triangle. That's exactly what I've written. Except I forgot to write down less than or equal to. That's important. Now, here, how many numbers do we have? Okay, and what we're assuming in this case is that our statement is true for when we only have k numbers. So this part right here is just less than or equal to a sub 1 plus absolute value of a sub 2 plus absolute value all the way up to a sub k, absolute value of a sub k. And then plus this guy here. So what I'm doing is replacing this quantity by a bigger quantity. And so it becomes bigger. And that thus, our original side, our original quantity we were starting with, absolute value of a sub 1 plus a sub 2 plus all the way up to a sub k plus 1. That's what we started with. Is less than or equal to this, which is less than or equal to this. So the original thing is less than or equal to this. Absolute value of a sub 2 plus all the way up to the absolute value of a sub k plus 1. And thus the statement is true by induction. Before I erase this board, does anybody have a question or comment? Everything okay? I think I have a comment on my question. I think it's tough to pick up everything in class for this material. Real tough. I didn't when I was a student. So it took a lot of time outside of class and then looking over notes and saying, what is this? And I wasn't a very model student in that respect. I kind of waited towards the end when we would have a graded assignment or a test, meaning a test. And it worked out okay, but it would have worked out better for me if I had been working all along because I could have followed in class a little better. But it still worked out okay. You know, I learned the material before I was tested. That's okay. The sooner we get it, the better it's going to be for us. We okay? Anybody with a question? Okay, I had said I was going to talk about something called Epsilon Neighborhoods, and they will be used throughout the class, of course, on occasion. Okay, so we need to know what we mean by Epsilon Neighborhood. So here's the definition. Given a real number, let's say x, and epsilon greater than 0, the epsilon neighborhood nobody in mathematics writes out the word neighborhood as I did, except the first time that they're defining it for you. And then what they do is they'll say epsilon NBHD, neighborhood. That's our abbreviation for it, okay? Epsilon neighborhood of x is denoted. Okay, so here's the way the book denotes it. It's V sub epsilon of x. a lot of times we use N instead of V. Our book uses V, but a lot of books use N for neighborhood. And is given by, so here's its definition. That's a symbol. But what it's defined to be, it's defined to be the set of all, I'll call them Y's. So it's all real numbers, Y, such that, that's such that, the absolute value of X minus Y is less than epsilon. That's all real numbers whose distance from X is less than epsilon. Remember, the absolute value of one number minus another number is the distance between those two numbers. Let's look at some examples. Let's just look at one, maybe. So let's say I looked at V sub 1 of minus 5. Somebody said, what is that? Okay. How could we explain this neighborhood? What is it?
Absolute value of -5 minus some real number that's less than 1.
Okay, so the way that we write this, that's right, that's good. So V sub 1 of minus 5 consists of all the numbers Y, all the real numbers Y. By the way, that's a beautiful bracket. For those of you who aren't looking, I want to point out, that's fantastic. Such that the absolute value of minus 5 minus Y is less than our epsilon. Less than our epsilon. What's our epsilon here? 1. That's not so beautiful, but anyway, it's there. Okay. So if you want, I'm going to go a little bit slower here. This is equal to the set of all Y's that are in real numbers, such that, well, this with less than, we had a statement with less than or equal to. Remember that A and C involving absolute value? This is what I'm thinking of in particular. So, absolute value of A is less than or equal to C, if and only if, what? With minus C is less than or equal to A, is less than or equal to C. But this statement, this analogous statement is true, instead of less than or equal to, it's true for less than as well. Is that okay? The same statement is true for less than. So here, I can rewrite this as minus 1 is less than minus 5 minus Y, which is less than 1. That's what we're writing it in this form here. And then if you solve for Y, let's see, I'll work on that. So I'm going to add 5 to both sides to get minus Y by itself. So if I add 5 to both sides, I get 4. Isn't that right? Okay, so I'm adding. So 4 is less than minus Y is less than, remember I'm adding 5 to both sides, 6. And now solving for Y, what would I do to both sides of that inequality, or all parts of that inequality to solve for Y? That's right, so I have to switch the inequality. So here, this is equal to the set of all Y's that are real numbers, such that it would say minus 6 is less than Y is less than minus 4. So you're looking for all real numbers that are sandwiched in between minus 6 and minus 4. Graphically, it's this. So, here's minus 4 here is minus 6, and it's these numbers. And I'm going to use open circles, so we don't include these infinits. And essentially, 5 is right in the middle. It's one of the numbers, not 5, but minus, that's right, I meant to say. Minus 5 is right in the middle. And what are we looking at? We're looking at all numbers whose distance away from minus 5 is less than 1. So it could be minus, oh, you could be 1 unit to the right or 1 unit to the left. Is that okay with anybody? Within 1 unit to the left. Interval notation-wise, this is the same thing. Minus 6 up to minus 4 comes with interval notation. That's what we're talking about. So that's what this neighborhood is. For this particular example, it consists of all real numbers whose distance away from minus 5 is less than 1. That's exactly what's meant by this notation. This notation. That's what we're talking about. That's all. Just the way we mathematically express it. Okay, so neighborhoods are going to come up. Wanted us to be aware of them. And the next thing I want to do is I want to talk about sets and give some definitions here. I'm kind of switching topics a little bit. When we're moving towards something called the completeness property of R. To do that, we're going to talk about some definitions about sets. So here's my first definition. I'm going to say let script S be a non-empty subset of R. So this is a collection of real numbers. That's what script S is. A collection of real numbers. Okay? Then the number U is an upper bound of script S if for all little s in script S, little s is less than or equal to U. What's that mean? To be an upper bound of a set, you're bigger than or equal to everything in the set. That's what it means. That's what we're saying. A definition that goes along with the previous definition, so let's see it, is what it means for a non-empty subset with real numbers to be bounded above. So definition, we're going to let script S be a subset of R, so it's a subset of real numbers that is non-empty. So that's the way I'm going to express this instead of the phraseology I used before. It's the same meaning. Okay? So S is a non-empty subset of R. That's what I just wrote. That's a period at the end of it. See, period. Script S is said to be bounded above. That's what I'm defining. Bounded above. If there exists, that's my symbol for there exists, an upper bound of script S. So if script S has an upper bound, called the set that's bounded above. Well, if we have this definition of upper bound and bounded above, we ought to have a definition for a lower bound and bounded below. So let me write those definitions down. And we'll do examples. After I write down what's meaning about it. So 4 more definitions. So here, we're going to let script S be a subset of R that is non-empty. Then script S is, I'm sorry. Then what I'm going to say, the number, I'm going to call it script L. The number L is a lower bound of script S, that's 7. If L is less than or equal to S for all S in B, script S. What is that saying? We're talking about a lower bound for a non-empty subset of real numbers. What's a lower bound? It's a number out there that's less than or equal to every number in B set. That's what we're talking about.
So from that, would we be able to say that for all S in that set of script S, that S would have to be greater than or equal to script L and less than or equal to U?
For what to happen?
For S to exist in the set?
Well, first of all, we're talking about U. No, that's not quite right. So you can have an upper bound and a lower bound, and just because you get everything in between them doesn't mean that you're in S. Everything in S is in between them if you have an upper and lower bound. But just saying that you're in between them doesn't mean. Okay? I'll show you an example in just a few minutes. But next I want to give a definition. So what does it mean to be bounded below? So we'll let script S be a subset of R that is non-empty. And we say script S is said to be bounded below if there exists a lower bound of S. I want to give 2 more definitions. A non-empty subset S of real numbers is said to be bounded if script S is bounded above and bounded below. And forget the word bounded, we ought to have the word unbounded. It's opposite. A non-empty subset. Oops. Non-empty subset, script S of R, real numbers, is said to be unbounded. You're going to love this definition. What does it mean to be unbounded? If it's not bounded. Is that okay? Let's look at some examples. And Corey, I maybe didn't interpret your question correctly. So let's first of all look at some examples. Oh no, I meant this. Okay. I said no to the question. Here's an example. Let's look at the set. Let's let script S be this set. Let's let it be from 2 to 4. Interval notation. So what does this mean? This means every number that's in between 2 and 4, not equal to 2, not equal to 4. That's what it means. So part A, 5 is an upper bound. Of script S. That's a true statement. 5 is bigger than or equal to everything in this set, script S. Is that okay? So is 4.7. That's an upper bound. Isn't 4.7 bigger than or equal to everything in that set? So is 4. So is 1,000. No, let's say this. 57. Why did I pick 57? Well, that's how many points Alabama scored in the basketball game on Saturdays. It's Alabama won versus Auburn, 57 to 55. And for those of you who don't know, I was at the game, and my mom kept pulling at my shirt for me to sit down because she thought I was being too obnoxious. She told me, just sit down, son. We're 70. We don't want to be embarrassed by having somebody next to us that's screaming all the time. So that's what happened. And I said, off the tickets. I can scream if I want to. Okay, so that's an example. Part B, I'm going to tell you that -3 is a lower bound. And I'm running out of room, but I'm going to say part C, script S is bounded. Because it's bounded above and it is bounded below. Sure can. Yes.
Okay, yeah, my assumption was that script S had one lower and one upper.
There is something called...
That would be part of the set. It would be the largest and smallest numbers.
Okay, yes. So I think I understood your question. So there are things out there we're going to learn about in just a few minutes called the supremum and the infimum that will be involved with your types of thinking here. We're going to get to them in just a second. Let's look at another example first, but I still don't think that the infimum and supremum is going to work from the way I understood your question, but we can get close to it. There's another example. Let's look at this set. Let's call script S equal to the set that looks like -1 over n union with the set of guys that look like n, where n is a natural number. Okay. So we're just talking about combining collections of real numbers. The first collection of real numbers combined. So this one, all of these types of numbers, plus all of these types of numbers are sets. So I'm going to write down kind of this type of thing. S looks like the following. It looks like -1 over 1 is -1. -1 over 1. That's what I'm looking at. Then another number in here is -1 over 2. Is that okay? -1/2. minus 1/3.
While n is in
All the way up,
minus it.
going on forever. 1 over a billion, you keep going, okay? And then eventually, you get real close to 0, but you don't get there. Then you move on to these guys, which are 1, 2, 3, 4, forever. That's what script S kind of looks like. Is that okay?
So you could say it's the set of all n's where n is not equal to 0, where it's n and minus n's inverse.
Yes. Minus n's inverse. That's right. It's also included. Yes. Multiplicative inverse. Yes, sir. Okay, so that's S. Now here's what I want you to notice. Note, minus 1 is the lower bound. Minus 1 is less than or equal to everything in this set. Minus 1 itself is in this set. Is that okay? Previously, I gave a lower bound of minus 3 in the previous example, but minus 3 wasn't in the set. Okay? But here, the lower bound can be in the set, so could the upper bound. Dalvin was saying something, I think, correctly. There is no upper bound for this set. There isn't an upper bound. There is no number that's bigger than everything in this set. We'll prove that kind of later, but I'm just writing it down. So what can you say about this set? So script S is bounded below. But not bounded above. So script S is unbounded. Okay. While we're playing around looking at examples, let's look at one more example. Gordon, I think this might help you. Let's let script S just be equal to 1 over B, such that n's an element in that. All right. Okay. So here, what does script S look like in terms of numbers? Well, it's got 1, it's got 1/2, it's got 1/3, 1/4, and it goes on forever like this. Note, 1 is an upper bound. Of script S. So 1 is bigger than or equal to everything in this set. Okay. Can you give me a lower bound? It has one. 0. And if it has one, it has infinite. But I want to tell you, 0 is not in this set. Is that okay? So if it has an upper bound, then it's bounded above. And since it has a lower bound, it's bounded below. So that means overall, this script S is a bounded set. This is great to look at. We're going to look at this a little bit more in depth. But Corey, I wanted to address with that example a little bit more what you were thinking, I think. But I said no to your question. You know, I got 0 being an upper bound for this set. I'm sorry, 1 being an upper bound for the set and 0 being a lower bound. But this set looks like this. So in our previous example, script S, pictorially, here's 0. That's not there. 1. 1's there. 1/2's there. 1/3 is there. And I keep going down. And I get real close to 0. But I don't get 0. Is that okay? Okay. everybody, this is not all the numbers between 0 and 1. Is that okay? There's big gaps. I mean, there's no number included in script S in between here. Is that okay? So, Corey, you just can't say, here's the biggest number involved, here's the smallest number involved, and it's everything in between, because it may not be. It might have some gaps. Okay, and that's what I understood your question. Okay, well, the thing that we're going to talk about next is the least upper bound and the greatest lower bound, but we'll save those for next time. So they're kind of more specific upper bounds and lower bounds. Right? Thank you very much.